All right. Good. That's working. I have about 2 hours to sit down and do a little bit of a tutorial. So I thought I'd just take the opportunity because recently someone asked how one does writes a parser in C++. And the example was a C-like language, which is any language that which is a good start for a language. So I've created a new project. I'm not going to go into how to compile a C++ project or how to do that with your IDE. I will be creating a bunch of files that will show up somewhere in the left, like one file per class or something like that. That's about it that you need to know about this IDE. This is a standard Hello World thing. And so the first thing we will do is we will create a file, just an empty file, like a test file. So we'll call this, I don't know, test.myc or something like that. And just a test file is fine. Okay, and so in this we will write the things that we want our programming language to parse. So for example, we probably want it to parse, well, let's leave away include statements for now because those are something else. Let's just go for a regular program. So let's say void main void curly bracket printf hello, it has been %d years since I learned C, \n. And then we'll go and put a little equation in there as well. So let's say current year minus, I think, 1995 or something I learned C. Something like that. So this is actually something that might run as a C program if you didn't mention the include statements and things like that. So it's a good example to start with. So that's what we want to parse. So how do we do this? Well, first, we need to read this program word by word, or rather character by character, because that's how we get it from the file system. And since we sometimes might want to look ahead a little bit to, like if we see void main, then the question is, okay, we know void is a type, and then we see main and we go, okay, this is some identifier, so probably a name of something that is this type, but now we want to know, is it a variable or is it a function? And so we need to look at the next letter and decide if it's an opening bracket, then it's the start of a function, and if it's a semicolon, then it's actually the end of the line, and it's probably a declaration for some sort of global variable or something. So we need to do this, and we might actually have to look ahead a little more. For example, if we see the word long, then of course next we will want to check, is it long int, or is it long int, or is it just long, which is short for long int but also permitted, things like that. So we might look ahead and then decide, no, we don't actually need this other token. And so if we scanned over each character each time and then repeated that over and over for each thing that we want to test, then that would be a bit slow and a bit annoying. And so what we are going to do first is we're going to break up the script into like the individual parts. So that means identifiers like void and main, operators like the opening bracket, another identifier, undo. and operators like the opening curly bracket, closing curly bracket, that thing, and of course strings. So a string for us, we don't really care at this point where we write the parser what is inside a string. All we need to know, it's a sequence of characters. And we just store that away somewhere, and then we pass it to whatever function. And in a traditional C compiler, a string passed to printf is just that, a string. The compiler knows nothing. Of course, in modern compilers, we actually have usually special code that looks at the % sequences in a printf and can provide you with additional error messages. But that's not the common case, so we'll ignore this. That's just some extra fanciness that you can add later if you want. But so that means, so what we'll build is an array of these individual identifiers and those are called tokens. So like a token is an identifier, an operator, a string literal, a number literal, and even like a floating point number would be another literal. Maybe that's something else. Let's do double foo equals 1.5, just so we have that as well. So we'll build an array of tokens that are equivalent to our script, and then we'll keep working with that. So the first thing that we want to create is a C++ class that we'll call Tokenizer. All right. And let's just prepare everything. So I usually use pragma once because all the compilers I use support that, and you don't need to do the #ifdef. And some compilers can be a lot smarter about pragma once than they can be about, if you use the #if include guard, then that usually means it doesn't really know that this is an include guard, so it has to run the whole preprocessor over the entire file. Whereas if you use pragma once, the compiler knows, okay, you just want me to only include this file once if it's included a second time. We'll use, just to be very clean, we use a namespace. This project is called Simple Parser, so that's what we'll call our namespace. And then we put our Tokenizer class into, oops, I just lost. All right. Luckily undo, let me recover. Okay, so give it a public method. So what the Tokenizer does is it has a parse method. So we include a vector because that's our list to which we can add stuff. And then we say, wait, inside the namespace, using namespace standard, so we don't have to type as much. And then we can just, by the way, you may notice the main advantage of this namespace, beyond just having a namespace, is that it gives us a scope in which we can use using namespace standard. So everyone who includes tokenizer.hpp doesn't get our using namespace standard leaked into their own code. So that's one of the reasons why I'll be using the namespace here. Oh, and of course, no, we don't need to do that here since it's already namespace simple parser. So we say vector, and now what we need, of course, is a class to represent each token, of which we can have a list. We'll fill that out in a second. Let's just write, okay, token parse const string in program. All right, so that's the method we're going to implement in a moment. Of course, we also need to, we also need to include string to get the string class. And now what are we going to do with the token? Well, for one thing, the token needs a type. So we have different kinds of tokens. So we say enum token type. And one type is, so here's the thing, we're going to use this for the parser itself. So one token type will be white space, which, you know, is not something we will ever create a token for. But it's a token type nonetheless. Just because we'll be using it during parsing, kind of as the unset state for our token. You'll see that in a second if that isn't clear yet. But the actual token types for which we will create tokens is, of course, identifier, integer, literal, string, literal. And now we have several choices. For right now, I'll just go with an operator token. You can also, of course, do this more fine-grained. Or what I've done sometimes is I've done a token type and then a token subtype. So I can say here, this token needs to be an identifier, and then the identifier subtypes would be things like, you know, like the for, the if, the do identifier, using namespace, kind of like identifiers that you might have in your programming language. Or the same you can do for operators. You know, you can have operator, you know, like, and then have, you know, like curly bracket as a separate operator, then regular parenthesis, so that one here, opening parenthesis, or you know, semicolon would be a different operator, or the ampersand would be a different one. With operators, you could also use a character constant here, because usually they are one character, but of course, as soon as you go to less than equal or something, even that doesn't make sense. Anyway, so you can do lots of things here. You can also have like separate types for, like, you know, like you can have a type for curly bracket because it usually opens a scope, you know, like, so you could have scope open operator, scope close operator for those. You could have, you know, like ampersand and other operators under generic operator, and then have semicolon separate because it's usually not, you know, that's fine. Do whatever you think makes sense. Right now, I'll just go for operator. Maybe I'll reconsider later. We'll see. But anyway, so, and then we have a token, of course, that has a token type. Then we have a string with a token text. So we'll just put a copy of our token's text in there for now. That makes it easier to debug, because if you have a token, you see what its original text was. You can also do fun things like have you know, and for strings, of course, we need it. But you know, you can also just put the operators in there and then compare the string once you know it's an operator or something like that, if you want to. So that's why. And what I usually do for error reporting is I put the start offset and end offset of a token in the token, and you can even go so far and put the line number in there if you want to. Since we're in C++, let's initialize them all here. And let's see, start out with white space, which is basically invalid. Okay, So now we have a token and we have a tokenizer with a function parse. Now we'll create a definition for that function. My IDE kind of generates a stub for me, which is a little verbose. So we go with namespace simple parser again, because then we can shorten this a little to make it more readable using namespace standard. All right, and now we can never get rid of the tokenizer, but the rest we can get rid of. Okay, so we have a tokens list here that we will fill, and we will return that list. So what does this function do? Well, this function just loops over the text in the program, and we build basically we're doing a standard state machine. State machine sounds scary, don't worry. If you have never heard the term, or have only heard it in complicated contexts, basically a state machine is kind of a way to save yourself from writing a lot of booleans. So usually you have a boolean, for like if you read text and you encounter 2 slashes, for instance, then you would say, okay, 2 slashes, that means it's the start of the comment, of a comment. And then you kind of would have a boolean somewhere saying, I'm in a comment now, so that you just ignore any text that comes there, even if it's an opening bracket, even, whatever it looks. And kind of to keep that state, that's what we do. For that, we will abuse our token because we're using tokens anyway. So we'll just have a current token variable, and that is empty right now. And then we're going to loop over our so current character in program. And now we just switch over the character. Now there is one thing I should say here. This assumes that our program is like C, basically pure ASCII. This doesn't really handle Unicode, because, if you wanted certain Unicode characters to be valid, for example, if instead of exclamation mark equal, you wanted to use the not equals letter, the equal sign with the strike through, that is like 2 bytes, so 2 chars when encoded as UTF-8. So if you wanted that to work, then you would have to write this code slightly differently, because you would have to recognize that this is a multi-byte sequence Unicode letter and extract it. Sadly, there is not much Unicode support in C++ right now in the standard library. There is a U8 string class that is supposed to be for that, but it doesn't really do anything right now. So that's why right now this is all just ASCII, and that's it. And now we just look at the characters. So we go, for example, case 0, case 1. So you see that's character constants. So that's just that character that we're switching over, of course. I'm trying to remember. I don't actually, I'll just do it manually for now. I think there was some syntax like 0 to 9 or something like that. But I'm not sure if that's, I might be mixing that up with Pascal or something. So let's just do each one explicit. 6, 7. We need 2 more. 8, 9. Of course, do a break. And so now here we know it's a number, and now we look at the current token. So if current token type equals white space, which is, you know, like the normal case, then we change the current token type to integer literal, and current token text append the character. That should work, right? Why is it saying it's not happy? Oh, is it 1 and character? Yeah, count. Okay. All right. So this shows me the name of the variable here, so I can actually tell whether I got it the right way around, you know, because it might be character or count character. So that's just my IDE showing me some text extra. That's why it's on a lighter background and in gray. That's not actually code I've written here. Just if you see that, just it's a help from the IDE. And otherwise, for now, we'll just append it as well. That means that, you know, if we're not in starting an integer, oh wait, of course we can do that for, where is it? For integer literal as well. No, actually we don't have to. Okay, so so all we do is if it's white space and it's one of those numbers, then we make an integer, then we start an integer literal token and append that character. Otherwise, we just append that character because whatever else it is, it might be happy. There is one more case we have to cover here. Or no, wait, there isn't. Yeah, right. So if it's an identifier, for instance, that can continue with numbers, but it can never start with. The parser is why that rule exists there. All right. So what else do we want to say? We want to do some operators. So we say, you know, like, what do we need? Curly brackets. Now, one thing I'll do here just for practicality is I'll put those near each other because not all source code editors are that good at recognizing, you know, that those brackets are just in strings. And if you just if you put them in pairs, then, you know, it will be confused only from here to here, and that will still look like a complete case statement and things. So oops. What else do we want for our source file? Let's see, what does it show? We need an equal sign, we need a semicolon, and we need a minus sign. Equal sign, semicolon, minus sign. That's our only operator. So you see, I'm not treating certain other characters. Equal sign, minus sign, semicolon. Oh, right, we need a comma as well. And so here, the thing that you do here is you do something similar, but you just say if token type is not string literal, because like an operator, even when it's directly after an integer literal, will you know, will end that token. So we'll say, let's just make an end token, current token. We'll write that call in a second, just because we'll be doing it a lot. So we set the type to operator and append that character, and then immediately end token again. And otherwise, like if we're in a string literal or something, we'll just append it as we did in the other cases. So now what are we doing? Create new function, end token. Yes, create. And it even created it. Nice. So my IDE is really nice here. I haven't used this IDE much, and it's nice to be able to use all these features that I can't use in some other projects in the day job. Okay, so what does end token? What is it supposed to do? Well, for the first thing, oh right, I forgot an argument. We also need to give it the token list. I'm thinking it might actually be a good idea to use... let's leave it like that. We could make these instance variables. So let's say vector token tokens, and that needs to be a reference, and of course token needs to be one as well. The reason is, of course, that we plan to modify it. Same here, and those are not part of the public API, so we'll make that end token function private. That's just because we only use it internally, and people, you know, who want to use our class shouldn't be confused by it. All right, so what do we do? So basically, we just say if token type is not white space, because we don't want to generate any tokens for our white space. Because, you know, in C, apart from splitting apart certain identifiers, white space is not really relevant. In C proper, at least. If you go and try to re-implement the preprocessor, then, of course, whether there is larger white space or not makes a difference. In like hash define, you know, you say hash define foo bar. I think the white space is actually relevant. So there are some cases where the C preprocessor actually works differently. But we're not bothering about this. We're building a simple C parser for now without the preprocessor. So yeah, and rather we're just building a tokenizer right now. So what do we do? If it's not white space, because if it's white space, then there's nothing, you know, we want to enqueue. Otherwise, tokens push back token. So we add a new token for this, and then we say tokens token type equals white space, token type text erase, because you know, we append to this string, so we need it to be clear again. Yeah, that's pretty much what we have right now. I think I'll fill in the offsets later, or you could do that as an exercise or something. We'll see how we do that. So what else do we look at? Of course, we need to handle white space, which could be a space. Just to clarify, so what does this do? This, you know, puts our finished token, if there is one, in the token list, and then resets the token to a clean state, basically, so that we can start a new token with it. That's all this is supposed to do, end token. And then we support all sorts of whitespace characters. So \r and \n. \n is of course the Unix line break. \r is used in very old macOS programs, or \r \n is the combination used on Windows, in Windows native files. You can kind of, be a little clever about handling them by handling \n kind of specially. Just checking if you're a \n and your current token is a line break that had a \r, then you just don't count the \n as a line break because you've already covered it for the \r. But if it's not, then the \n gets counted. You could do something like that. I'm not going to do this right now, but what we can do is current token line number, just add 1 to it. For now, wait, of course not for the white space and not for the tab. And so what do we do with this? Well, with white space, all we really do is we end token. It's current token. And with this one, we end token and increment the line number so that everything after it has a different line number. And of course, we need to initialize the line number to 1 because they're generally 1 based. You don't generally have a line 0 because this is something that you show to users after all. Like with offsets, you can do it differently. Okay, so this way we already count line numbers, which is kind of nice for error reporting. And otherwise we just end tokens, which is fine. What else do we want to do? Okay, and now we do the default case, which we'll just assume is identifiers for now. If you wanted to be stricter, you could go and do this like filter out that it's only A to Z in uppercase or lowercase. But really this way, by just saying the default case, you can actually get away with using Unicode, because everything that's not an operator or whitespace or a line break gets automatically treated as part of an identifier. Of course we can't forget, almost forgot that, we have to do string, of course, as well. So this is a little more clever because the start of a string and the end of the string use the same character. So what you do is basically something similar as up here, which is, in the case of the quote, is if the current token is not string literal, then we end token just to be sure, like if there, was an operator or a whatever, or a number or something that immediately got followed by a quote, then this will work and we'll make sure that we don't lose that token. And then we set it to string literal and append that character. Else, if oops, what is it? Current token type equals string literal, then we end the string literal token here. And we just ignore the quote character, so that way we've already removed the quote characters. So there's of course one more case that now we haven't done yet, which we can do, which is what do we do with a backslash? I'm writing 2 backslashes here for the simple reason that, you know, 1 backslash would be an escape sequence in the character literal, so that's why I need 2. And here, of course, what we do is, again, depending on the token type, if the token type is string literal, then we treat this character specially. Otherwise, we just, you know, take the backslash and put it yeah, the thing is, what do you do with a loose backslash in your code? Usually what it does is tell you to ignore the next character, I guess. I don't even remember what a backslash outside of a string does in C. Like in the preprocessor, it's used to ignore line breaks. So in this case, what we should probably do is we should end token and just make it an operator and then do something with it when we encounter it. Or should we? Yeah, I don't really know what it does, so I guess for now we'll just do it as a operator, and then we can always see type equals operator. And then we've ended that token. So right now we only support single character operators. There are different cases how you can handle this. Like you could glue together certain operators that you know, but if you remember in early C++, if you wrote a template, so like if you wrote a template of templates, so like template foo bar of t, you know, something like that. Or rather, you know, t1 and bar of t2. Then you had the problem that this was parsed as a right shift operator. And so because it just, you know, took the longest possible match, but it's actually 2 you know, greater than signs or, you know, end of template brackets operators. So what you always had to do is put that extra space in there. So since we don't, you know, C++ these days doesn't have that problem anymore, one way you can do this is just by saying, well, you know, we only generate 1 character for each operator, and the right shift and left shift operator is a special case when we look for an operator, where we go, okay, if it's a greater than sign and there's another greater than sign operator behind it, so we have 2 token operators basically. That's one way to handle it. You don't have to do it like that. But it's one choice that I think I'll do for now. Okay, so now, of course, we haven't yet handled what to do, so we switch. Oh, right. So what do we do now? We don't append the backslash here, of course. And what we rather have to do is we have to invent another token type. So we'll do some no token ever has this type. And now we do one that is string escape sequence. So that is the state we will go into once we've encountered a backslash, so that we know the next character is that. And while we're at it, also we will need a one line. Wait, we'll need a. I'll do that in a second. Okay, string escape sequence. So that's the state we will set. And now right. Now we need to handle this case specially. So one way to do this would be to make each of these characters handle it specially, but really we can just do it here at the start. If current token type, because it doesn't matter what character is escaped, you know, we need to treat it that way. So string escape sequence. If it is that, then switch the current character. And then, so case n means append \n. So that's basically the same, you know, that our source code is using here. We're re-implementing that now. So we need n, we need r for return, we need t for tab, we need, what else do we have? Backslash for inserting a single backslash. There are others, but we won't really need them right now. So we'll just add a default right now. Throw runtime error. And write unknown escape sequence. All right, we need string 1 current character, and let's put the backslash into the error message as well. In string on line and now what is the line? The line is toString current token line number and put a full stop at the end. All right, and we need to include the exception header. All right, now it should be happy. Yes. What was that? Whoops. Okay, I accidentally logged myself out by using the wrong shortcut. Was it this? No, that wasn't what I wanted. Jesus. Code. Reformat file. Control Alt Shift. Whole file. Okay, that looks better. Anyway, so so that means at the start, if we're in an escape sequence, we handle it or we error out. That's nice. Here we handle numbers. Oh, we've forgotten, of course, the case of floating point numbers. So let's do that. And there, it's a little more interesting because, like, a floating point number, if you look at it, to our parser will first look like an integer. And then there will be a dot, and then basically another integer. So every floating point number token will start its life as an integer. Or I guess since the US has this crazy for a 0 dot, they just allow dot. So in that case, we also have to cover. So either it starts with white space. That's actually annoying. Let's, I'm not sure I want to cover this case right now. Like you can, I guess we'll just do it. Although I'm kind of, I don't want to spend too much time on this parser, on this tokenizer. I want to get to the parser. So anyway, so what you do is if case is white space or no, wait. So integer literal is a special case we have to handle. So if it's a dot in white space, that really should be a special case again. So let's say we'll add a new case, potential double. Okay. And now we say if current token type equals white space, then we go into state potential double and append the dot. If current token type is integer literal, then we know that the dot means it's a floating point number. So we go into, do we have a state for double yet? No, we don't have one yet. So we make a double literal. Okay, so we set the type to double literal because we now know it will be a double, but we do not end the token here. So if it's white space, we don't need to end the token really. If it's an integer, we just morph it over. That's why we don't end the token. And otherwise, we of course do the same dance that we do for operators, because dot is an operator in C. So we say we end whatever the current token was. We set the type to operator, we append a period to it, and end that again. Why is it unhappy here? Oh, because it doesn't have tokens as its parameter. I forgot that. All right. White space, double. Oh, and of course, in this case, we need to handle string literal specially as just append. Or rather, maybe we should swap these two. Make the else case just the append, for the simple reason that there's a few no, wait, most types, no, it was the wrong way. Okay. So in most cases, we want to append to just, to use this as an operator. So if you have an, I don't know, an identifier or whatever, then you want to end that one when a period happens. But if it's a string or a comment, then of course you don't. All right, so here we are. Case dot is, I think, covered. And then one thing we need to do is at the very end, so that's at the end of the loop, outside the loop, before we return, we need to call end tokens one last time, for the simple reason that we might have, like an identifier or something that goes up to the end of the document. And that would otherwise not get closed because there's no other token behind it that will end it. Okay, and of course we need to cover the case of identifiers. So everything else, if current token type is white space, or integer literal. Actually, that's a bit incorrect. Like integers and doubles can usually have like an f, for example, lowercase or uppercase f at the end of a double to indicate it's, a double or a float. I'm not going to cover that right now. I'm too lazy. Anyway, integer, double, white space. Then we say end token it's current token again. And then we say current token type equals identifier, and we append that character. Else, for the other ones, we don't really need to end the token. We just append the letter to whatever it is. And so that means it either ends up inside a string or as part of an identifier. So I think we should be good. So that's the situation of a start. So I think we're good with this function now. One thing, right, we have handled the string escape sequence. One thing we have to do is, once we've handled it, we need to set current token m type to string literal again. And of course, we need to not execute anything else. Don't we have, what is the potential double case, right? That we need to cover as well. So if there's a number and it's white space, then that turns it into an integer literal. So copy, paste. If current token type is potential double, then now that we have a number, we know that it's a double. So we say double literal and append that letter. So we definitely know it is one now. And now we need to handle the case for everything else. So one thing we would have to handle is if we encounter a dot in potential double, then of course we would need to raise an error. I'll just do that this way for now. 2 dots. Oh, no, wait. No, then it would just cause be a dot operator at the end. That sounds fine. So multiple dots are actually handled. But this would be 2 dots in a row. So I guess what we'd have to do is if we end up here with a potential double, else if if token type equals potential double, what do we do with a potential double? So a potential double would be a number with a dot and no other number behind it. So 1.1 dot. I guess for now let's just handle it as double literal, because I think that's what the compiler will do. Like, I think it lets you say .5 and it lets you say 1 dot. But it doesn't let you say dot though. So if it's potential double, if token text compare dot equals 0. So if this is actually a dot, then we turn it into a operator. And that, I think, is, now we should have all those cases covered. And now we have one more case to cover, and that is comments. And again, comments are a little complicated because a slash is a division operator, 2 slashes are a comment. So again, we go case slash, and now we need to add another fake type here, potential comment and comment. And comment is also a type that will really never make a token of, but we'll still use it here. So case slash if current token type equals let's see, which ones do we want to cover? In general, if we hit a slash anywhere, so if we hit it in a string literal, then we just append it. Else, let's see, we'll need at least one more case. So let's see, if current token type is potential comment, so that means we've already hit 1 slash. Then that means current token type equals comment. and we will empty the text. The reason for this is we will collect the slash, the first slash, just in case it's a solo slash. You know, we've appended that. We will append that actually here. And set its type to current token type equals potential comment. All right, so the default case, if we come in, is we're in white space or after some other token or something, but not in a string. In that case, the first slash we'll see will switch us into potential comment mode. Then we append that to the token. And we, of course, end token, because the comment could be right after, you know, a identifier. Okay. So then we append this character, and now yeah. And so if we then hit a second slash, we hit this case, we're in a potential comment, so we say yes, it's a comment, and clear the two slashes out, so we collect everything else. And now what is the end indicator for a comment? It's a line break. So we go up to here, to the line break, and it already ends the token. And we, for all other token types, we collect the characters. So basically at this point when we call end token, we will end up here. And so we'll just say, if not white space, let's see. So if it equals comment, then we don't push back the token. And really, what we'll do is just for fun, we'll print out what do we say? Ignoring comment token m text. Oh wait, like this. So it is brackets. All right, and now we need to include IO stream, of course. All right, so this will make us not generate tokens for comments. And then, you know, we'll just reset to white space at the start of the next line, which is exactly what you want. Because really, comments cause, you know, like a break in any token that they are next to. You know, they're basically like just the return at the end of the comment. So now we have one more problem. What if, you know, there was, you know, it's any other case? So again, I'll just do that here at the start. Else if current token type equals potential comment. Okay, and now potential comment and cur character not slash, then that's obviously a character. So what we do in this case is then it's just a slash operator. We've already ended the token, so current token mtype equals operator, and now the single slash is already in there, so that's fine. If it's potential comment, that's fine because it's not inside a string. That can never happen inside a string. Mtype, and we end token again. Where do we have an end token to copy so I don't have to type it? Here, okay. And so we'll end token and not execute the rest because all we want to do is add this operator. Okay. We're good here. Next thing we need to do is go. Okay, we've used all our types. That's a good sign. We haven't used the start and end offsets yet. Never mind those. Let's just delete them for now. It's, it sort of works like the line number. Like at the start of any token, you have to write the number in there, and then when you end the token, you have to write the current offset there, so you know. Okay. So now we have two things. One, I want to do a quick debug dump, or let's call it debug print function. Let's be clean here. Generate a definition, and now say, one trick that is very useful when you write a parser is you will have a lot of constants that correspond to text. And so the simplest thing that you can do is you can do as token type strings. There are much more clever ways of doing this that I use everywhere, but this is a good start. Whoops. Here's the quote. So there are ways with macros and stuff to make this kind of like keep those lists in sync automatically and everything. I've blogged about it. Look up X macros if you're interested. Control Shift Alt L. Whole file. I don't know why it insists on. Yeah, this works. All right, so we have the important thing here is that this array has the index here is 0 and the value of white space is 0, and this is 1, 2, 3. They get automatically assigned, so you can just plug any token type in as the array index. And now you can go into the debug print and say cout token, and now token type strings type, comma space, and now we have the text, which we should probably put at least in quotes so we can recognize it. So those are, as you see, they're just quotes that we print out. They're not quotes in the actual text. So everything will be quoted. And then after that, we should put what do we want at the end? The line number, of course. Oh, and we need a closing bracket. Okay, so now we have a function that we can call. That's a const function, by the way. All right. So we have a function that we can call on each token. And now we can go and run our tokenizer for the first time. So simple parser 0.1. Just so we have something. We only need one endl because we don't need to flush twice here. We actually don't need to. Oh, well, no, that's good. Okay, so now we need to read a file. How do you read a file in C++? I have no idea. Let's do it like we do it in C. File handle fopen. And now I need to figure out what this one's path is. I think we had file path. Wasn't there a copy file path or something? Copy absolute path. That sounds good. Okay. So now we have this path, and we only need to be able to read it. All right, and then we go what is it? Seek fseek, right? Yeah. And there offset origin. Okay. fh 0 seek end. That's what we want to do, and that's the file size. And then seek set as the start. So go back to the start. And now we do how do we create? Oh yeah, right. We create a string, file contents, and now we say file size, comma. So, no, let's use spaces. Okay, so now we have a buffer, and now we read into that file contents. I think file contents had a data, element size, file size, file handle. Okay, we could do some error checking here, but I'm really lazy. So first what we'll do is just output this. And now we need to run our program. It builds, and it didn't work. Okay, so I guess we need error handling. If not fh, see error find file. Let's see if that's already what we need. No, okay, so it can open the file. Okay, let's just step through it with the debugger. What am I even doing? Okay. We have a file handle. All right. Step over fseek file size 0. Oh, right. This is not. I'm an idiot. Of course, fseek just goes to the location, and what we need is ftell. Fh. That should be it, right? Yeah, okay, and now you see it printed out our pseudo program here. So that means we can read the text. Let's just do it this way. All right, and now we include our tokenizer by creating a tokenizer. And a simple parser dot parse file contents and vector token tokens, and now we loop over those. And print them. Cur token debug print. Why did I uppercase debug print, by the way? Refactor, rename. Oops. All right, that's more consistent now. And so now when we run this, it should show us our list of tokens. Okay. And now you see, what did it do with our program? Oh, it wasn't quite correct, but void main. And then, so those are operators, identifiers, that's right. Then it did opening bracket, that's an operator. Again, void an identifier, closing bracket, curly bracket operating. You see there's no white space or anything between those. Double foo equals is an operator again. It recognized 1.5 as a double literal. And then, okay, with the string, apparently we're including the opening quote, which we shouldn't. So I'll have to fix that one. Oh, it actually didn't recognize the string at all. The space cut off. Oh, we haven't covered strings in the space case, I guess. Okay, so let's go to our tokenizer and see how we handle spaces, white space in general. Yeah, it just does end token unconditionally, which of course is wrong. If current token equals string literal or m type type equals string literal, or of course comment else and token. And so what do we do in string literal? We just append the character. And line break is fine. We don't really support line breaks in strings. We could, though, if we wanted to. So this is still not quite correct. So we still have the opening quote in there, by the way, but at least we've grabbed... Oh no, this is correct, actually, because we had a \n at the end, and it actually output that as a proper token. Okay, so... yeah, here, of course, we don't want to append the quote. That was the mistake. Oh no, wait, if not string literal. No, right. We make it a string literal, but we leave it empty. Now it's correct, sorry. And now as you see, like we have here, so these quotes, like you see, the operator is also, so there are no quotes anymore around this string. We've already removed them as we wanted to. And we have the string, and we've converted the escape sequence \n into a line break. Now here we have 2020 minus 1995, closing bracket. That looks correct, pretty much all of it. So now we have a list of tokens. So now, how do we parse this? How do we write a parser? So that's the next step. Now that we have these, let's create our parser class. New C++ class, parser. Okay. Pragma once. All right. So the parser, of course, has a parse function that takes a vector token tokens and namespace simple parser. I always hit Command C instead of Command V, and that causes this editor to just copy nothing if nothing is selected. I didn't know who thought that was a good feature. And of course, we needed to know about tokens, so include Tokenizer HPP. I guess we could put token in its own header to make it a little less of a dependency, but hey. Generate definition for function parse. Namespace simple parser. All right. We'll probably need a namespace declaration soon, so might as well write it here as well, as long as we're thinking of it. Okay, so how do we do this now? Well, first we need to think about how we could parse a program. So to parse a program, never forget to drink occasionally, especially when you're talking a lot. So we have different levels at which we can parse stuff. So if you think about it in C, the top level is where functions live or where global variables live. So that's the first level we read at. And then, of course, there is the level, where like function contents live. There's also the level where, parameter lists live. All of these we'll have to deal with somehow. So let's start at the top level and say, how do we do this? Well, first we can go and say, so we need a concept of a current token. So that means vector token iterator current token, and that's tokens.begin. And now while current token not tokens end. So we loop over all the tokens, sort of, but as you see, I'm using a while loop here. I'm not using a for loop here because we do not always advance one token at a time. We, depending on whether it's a function or whatever, we advance at how many tokens make up that thing. Like the entire function body might get skipped in one of these loops. Okay, so first, we'd say we need an identifier to introduce something. So that would usually be the type of whatever we're about to declare. So if we had, for example, if we supported structs or something, then, the keyword struct would be something. But in general, in C, it's an identifier of some sort. So why not make it a little easier for us and say, make a function let's say bool, no, let's say token expect identifier. Usually people use it something, call it something like expect. And we can even give it a specific string. Name. Okay, and of course that needs to be an optional. So we can also signal that we don't have an identifier. Okay, let's create this function. Generate definition. Okay. So now we go, oh, right, and we need the current token. That should really be an instance variable now. The others should have probably been one as well in the tokenizer, but I guess we got away with it because we only had one function. Okay, let's put current token here. Okay, now say if current token, oh, and tokens needs to be one as well. Tokens equals tokens. guess, no, let's say end token. That's what we really need. Equals tokens end. Because we really only need to know when it's an end. So if current token equals end token, then return null opt. So that means we have no match. Just so we know, we don't crash or run over the end of our array when we expect something. Now let's see. If current token type not identifier, then we also don't have a match. So we also return null opt. Do those two right at the start. And now we know that it's an identifier token that is the next one. So we say if current token text equals name, then now we need to remember the token, of course. Well, let's say if it's not name, that's easier. Also return null opt. And so now that this is left, we say, where can we copy the type? Here we need another iterator. So we say return token equals current token. And we skip that token once we found it and return the old token. All right. So that's what our expect identifier can do. Return token like this. Oh, so we could probably just say token current token. All right, so now we can say here, if expect identifier, oh, one thing, if name empty, or, okay, so what this does is it lets us expect any identifier by passing an empty string, or lets us match the actual identifier. And now we can say here, if, yeah, and here actually we want an identifier. So let's say token possible identifier. Wait, it's an optional token. Expect identifier. If possible identifier has value, then we know we have a type. We have a type. Then we'll get the next one, which should be the name. Oh, let's call it possible type instead of possible identifier. And then we say here possible name. Expect, oh, and we need to have a default. Give it an empty string. Empty string means match any identifier. All right. Possible name. And now here we can say, now we need the same, but for operators. So expect operator, type is operator, no wait, if not name empty, and current token text not name. That's what I want here, of course. I wrote it the wrong way around. And so otherwise, if it matches, then we're okay. And now, do the same thing again. Operator. And here we say we expect a bracket. We have a type. We have a name. Possible operator. We have a function. Okay, possible name, expect. Okay, and so that means we know now we have a function. So let's just print that out. We have a function and say print its name. Which is possible name. Text. All right. So we will probably get fun errors or fun mistakes after the first parsing, but we'll probably get an endless loop. So let's just say exit 0 here. And let that run and see what happens. Oh, we're not calling the parser, are we? Okay, so parser, parse tokens. We have a function, main. Okay, so that worked. We got to that point. So yeah, And that's basically how the start of a parser works. Because you can just, keep going there. And now, as you aggregate all these things, you can actually work with them. So the problem with parsing C that you might already see here is we're pretty much blindly just running forward. We know that pretty much everything starts with a type. One of the things that you'll end up doing is probably build a little table of types that you have encountered, like when someone defines a type, and make sure that whatever you encountered here really is a type. And then if you know that it's a type, or if you know, if it's not in your list of types, then in that case, okay, this has to be some other construct. Things like that. Of course, a type is not just an identifier in C, because you might have a type that is a template type. Then, of course, you might have to. So we should probably make this a more complex function. So let's go back here and say well, we're only doing C, right? So let's not go crazy with C++ types. So that means we still need we could do an expect type function, I guess. And that means we need some data structure for our types. So class type. And now how do we model this? Well, we could just say, in the end, well, every type gets some sort of name. And every type gets let's see, what do we do here? I guess in the end, we can reduce all types to other types. So let's do an enum built-in type. And so let's say we have int 8, uint 8, int 16, so that's the bit length of those, uint 16, things like that. Let's maybe just do the types we will need for now. So that's int and signed int. That's signed and unsigned char for characters. Then we have double. And then we have what else do we have? Of course, we have struct. So enum built-in type equals mtype. And then if it's a struct, it's a vector of type. Can we do that? Okay, let's see if C++ will let us do that. Actually, not sure, because that's sort of a recursive definition, isn't it? But I think if the size of vector doesn't depend on, yeah, it doesn't depend on the size of its fields, I guess, because that's on the heap, so it should be fine. Okay, never mind. So let's say we return a type from parse type. Again, let's not say parse type, let's call it expect type. And of course, we need a map of string to type. Types. Okay, and now we'll create a little constructor. Okay, and now we'll go and say int equals type, and we need a constructor for type, of course. Oh wait, can we just do this? Name type fields. Equals int type equals int32. Does that work? No. Okay. Then we'll assume sorry. Okay, now let's give type the constructor it needs. Type const string name, comma enum built-in type name type. Okay, so now we can create types if we want to. And unsigned equals unsigned int, and let's say char equals int 8 signed char. Okay, we don't really have that one yet. Int 8t, I guess, is what we can call this one. And as we have multi-character names, we might need to special case that. You could probably do that by getting type you know, giving type keys that have multiple words, and dealing with those somehow, various things that you could do. But anyway, so as an example, we initialize our list of types here, and then we go to expect type and create a function for that. And now we say map string comma type. Oh, we need to include map, of course, so we can look up types. So the main reason why I'm using this simple naming scheme is because we will add our own types, and those then will get, you know, will get mapped to these structs as well. So like if you declare a struct or something, then you would need this table and would need to be able to add new types in there. For the built-in types, it wouldn't be that important. Iterator found type equals mtypes. So first we should expect identifier. Expect identifier. If not possible type, then return null opt. So that means if we don't have a type, have an identifier, we can't have a type. Found types equals my types find possible type text. If found type not mtypes end, or actually if it is mtypes end, then return null opt, and else return found type second, which is the actual type we found. So now we have a nice expect type. Optional type. Expect type. And now, oh right, what we shouldn't forget, of course, is that void is a type as well. Void. Okay. And so now, if we run this again, will it work? No. No appropriate default constructor. Oh, right, of course, we created our own constructor. So built-in type equals void, just so array can create default items if it needs to. Okay, so it still finds a function, which means it found our type. So if we now modify our test program and say instead of void, we say foo, it should say it didn't find anything. Yeah. In fact, it will endless loop here because we haven't got a case where, you know, we don't have a type and we don't advance in the token list in that case. So we should make an error. But anyway, this works. And now if we say int main void, say we have a function again. So it already knows about types now. Let's switch that back to void. Good. What else do we want to do in the parser? So the thing is, of course, it gets a bit unwieldy if you do everything here in the parser. So it's totally fine to go, to try to call parse function and put all of this code into parse function. But of course, in that case, what you have to do is you have to backtrack. So that means this one has no value, no harm, no foul. It didn't consume that first token because expect type, if it returns null opt, nothing, then of course expect type does not give you anything. But so if there was no identifier here, we would have already advanced past the type. So in this case, we need to deal with the else case and say minus minus current token. Similarly here, where we're inside the operator, we would have to backtrack by 2 tokens. But once we do that, we can just grab this entire thing and say bool parser expect function. Let's say function definition, because that's what we have in our code. And then here we say return true. Wish I could type. And in any other case, we say return false. And so now, if expect function definition, then I don't know, do something else. Current token text, so CR unknown identifier current token text end line. Okay. So now we should have our error message. So first, if we run this, it should still run like before. No. Oh, we should have declared. Can I create new function? Yes. Okay, now I put it in the header, right? Yeah, it added it here. It's in the wrong place, but okay. And now, if we run it, okay, it's unhappy and it didn't exit, but let's just say m++ m current token right now. So it will just skip. Usually you would just throw an error here or something. Oops. Okay. Anyway, and now we change our script. Oh wait, unknown identifier. It still gives. That seems a little weird. Oh, no, that's the rest of the function. Okay, yeah, that makes sense. So it successfully parses void main opening bracket, and then of course it chokes on everything else that we're not reading yet and logs it as an error. That's what we want, basically. That's good. We have achieved our beginning. And now what happens if we say foo main void? Now it should basically log the entire script. But it doesn't. Huh, okay, so our backtracking is still wrong. So let's see, what would that be? Expect function, expect type. And it would already fail here and return false, wouldn't it? Okay, let's just walk through, I guess. Run it in the debugger and see where it's going wrong. Okay, we're stopped here. So we step into expect function definition. And that does expect type. And expect type expects an identifier. Oh, that already consumed the identifier. So of course we need to backtrack here as well. So if not possible type, that's still okay. And here we don't find the type. So what we need to do here is a little more than just bail out. Minus current token. All right, now it should work. Stop and rerun. And what's happening now? Yeah, unknown identifier foo. So it already fails really early. And we don't have a function. So basically now we've implemented backtracking. And, you know, we have a basis for parsing types. So what you would do now is, you know, you would expand that with more function. Like instead of expect function definition, you would write another one that checks, is there a semicolon after it or an equal sign? Then that means it's a variable declaration, and but it's basically the same code. And of course, then you would parse the expression afterwards with a new function, because expressions are basically always the same. So that's basically how you would write a parser. I didn't really get to the part of nesting this time. I'll see if I have some more time. I might actually create a second episode of this. I hope this has already been a little bit helpful. So hopefully see you another time. Bye-bye.